Welcome to Time to Talk Science and Medicine. This podcast is brought to you by the Translational Institute of Medicine at Queen's University, Kingston, Ontario. My name's Dr. Charlie Highmarch, and I'm an assistant professor and researcher at Queen's University.
And I'm Dr. Stephen Archer. I'm a cardiologist and clinician scientist. I'm also the director of the Translational Institute of Medicine here at Queen's, which is called TIME.
In this series, we are fortunate to talk science and medicine with some of the most accomplished translational researchers from Queen's University and beyond. We want to know what their dangerous idea is, which is the concept that they're working on that, if true, would change the direction of research as we know it. But we also want to find out a little bit more about the person behind their discoveries. In previous podcasts, we've sat down with clinicians and basic scientists from Queen's University and beyond to discuss a diverse range of research, including cancer, cardiovascular disease, bleeding disorders, and animal care.
Today, we're very lucky to invite a guest from outside of life sciences. Most of our translational researchers, including myself, are busy working on understanding the human world. We're busy working on the building blocks of life, DNA, RNA, and protein. Our guest today is, on the other hand, trying to understand subatomic particles and the origins of matter and the building blocks of the universe. We're very proud to introduce Dr. McDonald to our podcast today. He's the recipient of the 2015 Nobel Prize in Physics for his work on neutrinos. Dr. McDonald, thank you for coming into our podcast today. And before we get too deep into your important discovery and your plans for future research, I'd like to ask you about your origin story. How was your journey from the east coast of Canada to a Nobel Prize in Stockholm? How did that happen?
Well, I was pretty amazed when it happened, but certainly didn't have that in mind when I started out from Sydney Academy in Sydney, Nova Scotia. I had a great math teacher, Bob Chafe, who really inspired myself and many others to love math. In my class of 35, there were 3 Ph.D s, actually, 2 in math and myself in physics, which is, of course, very much based on math. So I went to Dalhousie from Sydney to study anything I could use math in a creative way to do, and tried a number of sciences in the first year, and physics just clicked with me. It was something that I could do and that I really enjoyed. And these days I often get from student audiences at various levels, right from grade school on up, how do you choose a career? And I say, think of something that would be fun to do when you get up in the morning. Get a bunch of them, try them out, and see what you're good at. Put the two together. And that's essentially what I did, put the two together. I liked physics, and I seemed to be good at it. So I went from there to Caltech in Pasadena, worked at a laboratory that was headed by Willie Fowler, who eventually got a Nobel Prize for working out all of the nuclear reactions for the reactions that power the sun. And it was a very stimulating place. I then went to Chalk River Nuclear Laboratories in Chalk River, Ontario. And but I was doing basic research using an accelerator there, and then was got an offer from Princeton University in 1982, and was there until 1989. In the meantime, I became involved in the Sudbury Neutrino Observatory project. One of the leaders of that in the first place was Professor George Ewan here at Queen's, but he was about to retire shortly after 1989, and they were looking for someone who had experience both sides of the border. It was an international project, and so I had an offer from Queen's, which I took and gave up that tenure position at Princeton for another one here at Queen's, and came back here in 1989, and I've been very happily here ever since, working on this project, which, thanks to 100 or more other scientists, won the Nobel Prize in 2015.
And we're going to talk more about that discovery, but it's interesting. I wrote a little piece about lessons learned from the lives of Nobel laureates, and one of them was the clustering effect of Nobel laureates. And I know that wasn't your goal. You were just setting out to do physics, and it happened along the way. But you mentioned several highly accomplished people, including Nobel laureates that you worked with. It reminds me of the story of the discovery of the EKG, where there was a scientist named Gabriel Lippmann who invented color photography, or the chemistry underlying color photography. He was also the person that introduced Marie Curie to her husband. And Einthoven, who's the fellow that invented the EKG machine and got the Nobel Prize for perfecting the string galvanometer, actually benefited from this whole trajectory, starting with Gabriel Lippmann. So I don't know if you have any advice for young Canadians in terms of, if you're in Sydney, Australia, or Hampton, New Brunswick, wherever you find yourself, do you think moving to where the great ones are is an important thing, or can we do that all at home here in Canada?
Well, first of all, my first bit of advice would be, don't set out to try to win a Nobel Prize.
Mission accomplished. Thank you. Thank you for that advice. Charlie and I.
I'll drop that one off.
No, I mean, the Nobel Prize was icing on the cake. All of our scientific team were most satisfied with having come up with a result which was worthy of a Nobel Prize. It was a scientific result that had been a puzzle for many years, and we were successful in answering the question and creating a part of our full picture of how the universe has evolved since the Big Bang, a picture particularly that tells us how the elements are generated in the nuclear reactions in stars. Carbon, nitrogen, oxygen are generated in stars like our sun, actually. And so it's a part of where we came from. That's the objective, is to do good science in whatever field you're in. Very few people get Nobel Prizes. A lot of people deserve them.
Yeah. And I think that one of the things is that in my laboratory, there are centrifuges and there are fancy microscopes. But as you begin to tell us about your discovery, maybe you could just tell us what your laboratory looks like.
I will. But let me add one sentence to the previous thing. Another thing I often say to young people is choose your collaborators well, and be a person that is easy to collaborate with, because you can get so much more done in life if you have other very accomplished people working with you, and that's certainly what happened with me.
I think it's I love this question that we ask on our podcast, the origin story, because I think that we originally set out to try and find out about where you came from, but what's fallen out of all of the conversations with any of the speakers that we've had into our show is two aspects of mentorship and collaboration. And they seem to be kind of like the building blocks of any successful career, whether it be related to a Nobel Prize or otherwise. Everyone always cites a high school teacher or a university professor. And I think that's one thing that I think that young students need to kind of grasp, is the idea of it's the teams that you're actually working in that are far more important. And team science is increasingly becoming more important in Canadian and global science.
It is. And the things I am involved in these days, in fact, have been primarily since early 1980s, are large-scale international projects, because it turns out that some of the questions that are ranked at the top of the most interesting things to try to answer are things that require large-scale projects and many people. The ones that I've been working on are what are the basic properties of neutrinos, one of the basic building blocks along with electrons and quarks. And now we are moving on to attempt to understand the dark matter particles that we know exist in our universe because of their gravitational effect on our Milky Way and on other things across the universe, but we don't know what they are. They don't fit into any of our normal theories of matter. And so very fundamental things, but very existential in their nature also.
I was gonna say, sort of, actually, just right off the bat, as a biologist, is there a simple explanation for what dark matter is, or what it isn't, or what we know about it?
No, and that's the whole point. We really are, not to overplay it, but we're really looking in the dark as to what it is. So it is actually what our research is primarily, one of our parts of our research is primarily focused on right now. And so let me give you a picture of what we do, and it'll have in it a question of, what is dark matter and how can we attempt to address it? We are fortunate to have in Sudbury the lowest radioactivity laboratory in the world. We have a laboratory which is 2 kilometers underground in an active nickel mine in Sudbury, owned by Vale Corporation, and they're kind enough to allow us to have an ultra-clean laboratory with detectors the size of a 10-story building excavated in this region, which is kept in a Class 2000 ultra-clean environment that's close to the specifications for clean laboratories for making computer chips. Cleaner than a hospital operating room, since this is a medical program, to put it in.
You had to get that dig in, didn't you?
It wasn't intended to be a dig. It was something that people can appreciate, that they can relate to. But having that low radioactivity location enables us to detect very rare processes. Having the 2 kilometers of rock above us gets rid of the cosmic rays that otherwise would make our detectors glow like the northern lights. Similar processes happening in the atmosphere, and we're 1 million times suppressed for the cosmic rays coming in by being so deep. So what we looked for before were particles called neutrinos, or highly penetrating particles that can come out from the center of the sun, and they're made by the nuclear reactions that power the sun. By observing them, we can study those reactions. And as I mentioned, they're the ones that are basic building blocks of the periodic table. We observed 1 an hour in a detector the size of a 10-story building. I did that for about 9 years. And in the process of that, we were able to determine, first of all, that the calculations of how the sun burns are very accurate. And that's of value because we're trying to reproduce that here on Earth. We're trying to confine the sun in a bottle in so-called fusion power reactors, and the calculations you do are similar for the sun, confined by gravity, and for fusion power, confined by magnetic fields. So there's value, as usual, in basic science, ultimately, for humankind in one way or another. The thing that we have that was what enabled us to obtain the Nobel Prize, because we also observed properties of neutrinos that had not been predicted within the so-called standard model for elementary particles. And so it was revolutionary in terms of our understanding at a very basic level. But we've now moved on to attempting to see further properties of neutrinos, symmetry properties, which we're doing by having converted the original Sudbury Neutrino Observatory, or SNO experiment, to what we now call SNO Plus. We're dissolving materials, in this case tellurium isotopes, in that detector in such a way that we can observe a very rare decay, which would be very indicative of certain symmetry properties of neutrinos, which are important, in fact, to try to understand why it is, and in the Big Bang, when we think that equal amounts of matter and antimatter were produced, that we now have a completely matter-dominated universe. And so a fundamental question that is existential in its nature again. Dark matter is a very unusual material because it doesn't behave like neutrinos or any other particle in our particle zoo, which is very well understood up to a certain point, and it doesn't fit in it anywhere. But it certainly interacts through gravity, and we see that because if you look out on a starry night, the space in between the stars contains about 5 times as much mass as the stars themselves that are glowing. Stars we know are made of ordinary matter like us, This other stuff doesn't behave like that ordinary matter, but gravitationally it holds the stars in a pattern which, if you could look at the Milky Way from the side, which you can't, Milky Way is like a pancake, and when you look at the sky, you're looking through the pancake, and so you see a band of stars across the sky. But if you could get off to the side and have a look at it, it kind of looks like a cinnamon roll. It's a spiral. The stars in the outer reaches of that spiral are going so fast that you need 5 times as much gravity to hold them in their orbits as the glowing matter can provide. And that's one of the evidences for something else, which we refer to as dark matter. It's pervasive. You can make measurements across the universe and see the same thing. So we know it's there. It's in our galaxy. And if it is in the form of particles, they must be very massive, and they must be very weakly interacting, even more weakly interacting than neutrinos. In other words, they can pass through much more material than neutrinos can, even before you observe them. So having the lowest radioactivity location in the world gives us a tremendous advantage. We can put in materials, and we do it with a variety of experiments that professors here at Queen's are very actively involved in, that present materials to this set of dark matter particles that are there in our galaxy, and we're moving through these this clump of dark matter particles, and we're also going around the sun, which gives us motion relative to those particles. So what we look for is collisions between the dark matter particles and things that are in our detectors. And just referring to the set of experiments that about 6 or 7 professors here at Queen's are involved in this laboratory, one of them, if a dark matter particle hits the nucleus, a bubble is formed. And they can use that quantitatively to study interactions typically on fluorine. We do one which is liquid argon, 3 tons of liquid argon in this underground location. There, if it's a dark matter particle, the light comes out in 10 nanoseconds. If it's a radioactivity, then it comes out over 500 times longer period of time. And therefore, we can discriminate against radioactivity, any residual radioactivity, by a factor of about 100 million. And so all of these experiments have a trick to try to see dark matter uniquely. And if we can identify how dark matter interacts with ordinary matter, then maybe we can understand where to place it in the theory of everything as we are looking, which we are looking for. Again, an existential question, because just using gravity, we have a pretty good picture of how the universe has evolved to its present form over the last 13.5 billion years. Turns out the Bare Naked Ladies got it right in terms of the number that they quote at the theme song for the Big Bang Theory. And the Big Bang Theory has been validated in a tremendous detail. And in fact, a Canadian, Jim Peebles, got the Nobel Prize for doing this about 3 years ago. He's a graduate of the University of Manitoba and a professor at Princeton for his whole career. So we know pretty well how the universe has evolved to its present state from the Big Bang. We don't know what happened before that, but it's an existential question, not just the existential questions you're asking about how humans have evolved, which are very important as well, but rather how has everything evolved? How has it come to be? How has this universe in its present form been created, at least since the Big Bang? And that's the basic motivation for all of this work that we do in these unusual particle physics, almost imaginary world that we work in, because no one has ever seen a neutrino. They've seen a flash of light in a detector indicating they're there. No one will ever see a dark matter particle. Again, flash of light, bubble. but the framework sticks together very well, and that's what we're trying to do, the next piece.
There's actually an interesting parallel with molecular biology because, as I say to students, it's this tiny microliter volume contains DNA or RNA, and we're going to add some more volumes of clear liquid, and then we're going to do these processes. And really, it's the end point of what we find, which is a signal, which is an indirect signal of what's going on. But ultimately, you never really see the DNA or the RNA. You just have an indirect measure of the fact that it's there and it's operational.
It is interesting when you describe the Milky Way as a cinnamon roll. It reminds me a lot of a cell, because if you look at a cell, it's full of structures, which would be like particles, but there's cytosol in between. And that cytosol, your description of the dark matter sort of reminds me a little bit of the cytosol of the cell, with all the matrix and the materials, the proteins that float around in that soup that particles interact with. And I guess, as someone who went as far as Physics 101 at Queen's, is there any chance dark matter is not a particle?
Yes. Mm-hmm. There are other forms that are they're very different in their nature. One of them is called an axion, and it would result in dark matter formed much earlier following the Big Bang, and taking a very different form, and it's somewhat particulate in its nature, but it's actually detected by looking for it as a essentially electromagnetic wave. You look for it to interact with combined electric and magnetic fields rather than producing a burst of light.
So I may have to take Physics 201.
Maybe. See if we can understand.
Maybe I'll see if I can
Maybe we'll repeat 101.
Welcome anytime. I'll trade you for a little bit of
Dr. McDonald has actually given his talk on neutrinos at Medical Grand Rounds, and we awarded him a stethoscope. So I'm not sure if he'll award me a square foot of the detector in the SNOLAB. But yes.
What I really need is someone with your expertise to use that stethoscope when I need it.
Yeah, well, you have a standing cardiology free pass.
Yeah, absolutely. Okay, so I mean, thank you very much for the very detailed explanation about the kind of the role of the SNOLAB in sort of finding your discoveries, and it's kind of interesting that, just to summarize, the fact that it's so deep underground and with such a low radiation, it's a background to signal ratio that you're trying to achieve.
That's right.
But I'd just like to kind of redirect the question and have you answer it once again in terms of kind of, what are the building blocks of life and what's the discovery of neutrinos, but to treat us like we were high school students. And it's not to dumb it down, but just kind of distill the information so that it's super accessible for our audience.
So let's talk about neutrinos first. Scientists are always careful to say, as far as we know so far, the three basic building blocks are the parts of what's called the standard model for elementary particles are electrons, quarks, and neutrinos. Electrons, of course, we all know, they're what run in the wires that power our world. And they basically, they're the outer parts of an atom, and therefore they define all chemistry and biology and everything else. And they generally are dominantly interacting through what we call the electromagnetic force. There are also what's called quarks, which are inside protons and neutrons, which are themselves inside the nucleus of an atom, around which the electrons revolve in making up a chemically active substance. Quarks, as far as we know, do not get out of the neutron and proton. The force is infinitely strong if you try to knock them out, but they have residual effects that are the nuclear force. And there are 3 of them in any proton, 3 of them in any neutron, and the charges are a third so that they can be added up to be either +1 or 0 for the neutron. Neutrinos, on the other hand, are a very different thing. They're only really evident in a radioactive decay, actually, when one quark turns into a different type of quark. We see them in radioactive substances. They are emitted when the sort of radioactive substances that are used in PET scanners, positron emission tomography scanners. When you inject radioactivity into someone to then observe where it goes within the body with essentially cameras that take advantage of the properties of this radioactive substance. They are also being emitted at the same time, but they very seldom interact in anything. They are able to penetrate from the core of the sun through the very dense material. If you had a chunk of lead, which is the equivalent to the distance that light travels in a year, 1 billion kilometers, the probability that a neutrino would interact with it is only about 50%. So once in your lifetime, a neutrino might stop in your body, change one atom, you won't even notice it. The basic properties of these neutrinos were still, many of them, unknown at the time we started our experiment. What we observed is that the neutrinos produced in the sun, one of 3 types, which appears to be the structure of this standard model, 3 types of quarks, 3 types of neutrinos, 3 types of electrons. The other types are only observed in higher energy collisions and cosmic rays and from accelerators and cosmic rays and so on. We observed the type of neutrinos produced in the sun, one of the 3, changing into the other 2 types before they reach the Earth. That can only happen if neutrinos have a mass that's greater than 0, a rest mass as we call it. And so we've added basic properties of neutrinos to this standard model, and that's actually what the Nobel Prize was awarded for. The question of how that fits into this overall picture of how things have evolved since the Big Bang is part of the objective of what we do. And so they're very difficult to detect. We built a detector that, as I said, is the size of a 10-story building. We borrowed 1,000 tons of heavy water from Canada's reserves. Heavy water is used as a way to slow down neutrons in a Canadian nuclear reactor. It's a unique design. And this particular amount of heavy water was valued at $300 million. We put it in a transparent vessel 2 kilometers underground, and we had to show that we were going to do it safely, which we did. And it was a unique experiment for Canada. So that's the basis of the particles and where they fit into the standard model. The way in which the universe evolves is another whole question. And there we think there was a tremendous Big Bang where energy is transformed into mass, E equals mc squared. We don't know the origin of that tremendous amount of energy, but it was a temperature of something like 10 to the 30 degrees Kelvin or something like that, enormous
That's warm.
temperature and energy. And over the first 300,000 years, basically, the original blast produced the basic particles, electrons, neutrinos, quarks, and their heavier counterparts. After about a microsecond, they had formed into protons. After about 3 minutes, they formed into nuclei. The protons and neutrons formed into nuclei. And after about 300,000 years, those nuclei picked up electrons because things had cooled off from the tremendous expansion after this original explosion. And at 300,000 years, you have atoms formed. It's then neutral. Light will transmit through it. And amazingly, people have measured that background light from the original Big Bang with exquisite precision. In fact, the snow on televisions and early television sets had a few percent of that particular radiation showing up on them. It's still there. It's there today, but it tells us a lot about what things were like 300,000 years after the Big Bang, and we can learn a lot about the details of what I was just describing by measuring that, and people have done it.
Yeah.
And actually, that leads nicely to our next question, which is about the dangerous idea. So, and we've talked a little bit about this because we've met many times before, but the concept of pursuing existential questions. And, so maybe you could tell us about your dangerous idea and the idea of what scientists should be doing, and maybe not answering the convenient question, but the existential question. What do you mean by that?
Well, in any field, you are attempting to make a measurement that's going to be of significance at the cutting edge. In medicine, you're trying to understand what are the most important problems that will have the biggest impact if you can get an answer. Well, in our case, we're fortunate to have this laboratory that we developed for the original Sudbury Neutrino or SNO project that is world-class. It's attracting very major experiments from around the world. And in every case, people are motivated by the fact that, we have this model for how the universe has evolved since the Big Bang, which is very well described by, for example, the distribution of that radiation from 300,000 years after the Big Bang. In other words, 13.2 billion years ago. It's very explicitly described. Many other things are measured by astronomers using the satellite-based instruments. We are using particles, and what we do is what we call astroparticle physics. And in fact, we have an institute here at Queen's, which is partnered with 10 other universities across the country to support the academic side of that science to go along with our laboratory. So what do you want to aim your work at? Well, the things that come at the top list of what's the most important questions in physics. And two of them are, what are the further properties of neutrinos and how do they fit into how the universe has evolved? And what is this dark matter stuff that we know is there, but we don't know what it is? And where does it fit into the theory? And how does it affect? We know it affects the way in which galaxies and stars are formed, which is then gets down to how our sun is formed and the nuclear reactions that make up the elements that we're made from. So they're important questions, and they're big enough that you can convince hundreds of scientists to collaborate to try to answer them, and sometimes convince the government to put the money into it.
And when you call them existential, are they existential because of the beauty of the science? In other words, it's a fundamentally attractive question that we human minds need to get our heads around. Or do you define existential because it changes life on Earth?
It doesn't change life on Earth. It explains why there is life on Earth, and not completely, but it explains where all of the elements that make up the Earth and the way in which they were all developed, starting with this major explosion 13.5 billion years ago.
That reminds me, there's a song by an American satirist named Tom Lehrer, which is called The Periodic Table. And my wife has forbidden me to play it anymore at dinner parties, but basically he has a great line in which he says, these are all the sort of elements that have been discovered that have come to Harvard, but there may be others that haven't been discovered. And so maybe you'll answer Tom Lehrer's.
Tom Lehrer is he's an icon for the scientific community in terms of his.
Maybe I should have you over for a cocktail party.
Yeah, you get to play the song.
I would say, go and play it again.
So I was going to pull on the tag of existential questions, because I think that as a scientist in my field, I can't think of many existential questions that kind of anybody's trying to attack now, probably since the 1950s, where people were starting to be attracted from all sorts of other fields of science to answer this, what are the building blocks of life? And actually, Francis Crick, who was kind of one of the people who helped describe the kind of double helix based on Rosalind Franklin's data, he basically came from physics originally. And he was one of many people who flocked to this field to try and apply what they knew. And I'm kind of thinking about that whole the interactions between the different sciences are actually what is most important in facilitating. So another Nobel laureate, Peter Midwa, wrote this phenomenal book called The Limits of Science. And there's one line that I think our audience might appreciate, which is that the demarcations in science are for administrative purposes only. And that was an early recognition of the fact that actually, even the conversation we've had here, we've been sort of dipping between physics and then back into biology and medicine through descriptions of PET imaging, for example, being an application of physics.
There's been tremendous collaboration between physics and biologists and medical people over the years. I mean, the technology that even back in the 1970s, we were using some of the first computers that were available, programmed with paper tapes. PDP-1 was the computer we were using at Chalk River when I was there, and I was just amazed. About 4 years later, to visit a friend of mine who was a neurologist at University of Western Ontario, who was showing me the same computer, the same sort of gamma ray detectors that we were using, but they had set them up in such a way that they were coupled to an ECG. They were showing imaging of the heart, and they could use them to determine faults in the person's heart. And that's really another strong motivation for attempting to develop new types of detectors. We have a type of detector that we're using in dark matter research that is valuable, we think, in reducing the amount of radioactivity you have to use in PET scanning by getting better resolution, and therefore you could use lower doses, which might enable younger patients to be used, because these days you worry a little bit about putting heavy doses into young patients. So the collaboration back and forth is very valuable. The 21st century, I think, is expected to be a great, let's say, step forward in both medicine and biology because of the understanding of the human genome that occurred back at the beginning of the century, and the use of rapid ability to understand the genetics behind various things in medicine, illnesses, and so on. People talk about personalized medicine now based on what you can learn quickly, and that's a strong collaboration between physics and medicine in terms of being able to do that.
Absolutely. A lot of the infrastructure we use in QCPU and in all of our research is fundamentally based on sort of technological advances that are outside of the biology spectrum. I mean, we can sequence genes based on the fact that we have infrastructure that can do this, which relies on a whole host of different sort of physics applications.
And I'm sure the people that have developed these pieces of instrumentation regard what they're doing as existential in itself. They're saving human life.
Of course.
And it is interesting. I think of the arts, forgetting the sciences, but the arts in Joni Mitchell's song, which talks about we are stardust, we are golden, and sort of looking back to the stars to explain us. And I guess your existential research is, where did all the particles that became Charlie Hindmarch or Art McDonald, where did they all come from? And
well, it's even more explicit than that, because it turns out that the early stars developed through a sequence of reactions, nuclei up to a certain point, typically around iron. And then those stars collapsed, forming a supernova, distributing all of those elements into the interstellar medium. Those then came together in the future stars, and then you began to build up the heavier elements beyond iron in the future stars. And so, in fact, the stars these days are made of stardust, and the elements we are made from are a part of that as well. So she's literally scientifically correct when she says we're made.
Joni Mitchell, if you're listening, I want your autograph, and congratulations.
So building on our conversation about kind of collaboration, because I think that we both appreciate that. We were both in the Canadian Science Policy meeting last week, which had over 1,000 delegates of scientists and civil servants and the scientific community. How important do you think the idea of a national framework in Canada is to be able to kind of draw these kind of beyond the ingredients of science, draw these together so we can actually start connecting the dots?
Well, that meeting is an excellent forum for a discussion of very important questions in all fields of science. I think there were 1,000 delegates at the meetings last week, which we both attended. I was actually on a panel that discussed a new framework that the government is putting together to try to regard all of the national facilities, major research facilities as they call them, as national assets, as things that need to be managed in a portfolio with a life cycle perspective on them to try to maximize the output from these facilities. Facilities, when you're talking about a major thing, SNOLAB is an example, are ones that have, by peer review, been decided as being places where Canada can excel. And so having the government pay attention to the point of saying, we're going to manage them as effectively as we can to make sure that Canada does excel and collaborate with international. A number of them were built in a CFI program, which was to build labs in Canada that will attract international scientists to collaborate. And they have been, SNOLAB is one of them, Ocean Networks, an underwater system off Vancouver Island is another, Amundsen Icebreaker for study there in the Arctic. They're all designed to try to enable Canadians to collaborate internationally. But even more important, in the April budget, which the government put forward, which had a strong scientific component in it, where they announced extra funding for the agencies that give out funding for academic research across the full spectrum of research. They also announced that they are appointing an external advisory group on science and innovation, which we are expecting will provide a roadmap, a strategic plan for how Canada directs its resources in science and innovation to get the maximum of basic science and the maximum of applied science in terms of commercial output, working with the companies that do research in Canada. That's something that I think will be of great value for the country.
Yeah, I think one of the lines that kind of resonated for me from that conference is somebody stood up and said, strategy needs to come before resources, so that you understand how you're going to effectively use those resources to drive the outcomes of that strategy.
Yes, actually, Minister Champagne was quoted, what he said was, today's research is tomorrow's products.
Yes.
And that's a perspective that it's very good to see the government feels is true.
Yeah, it is very interesting. And I think we often suffer from not maybe having enough guidance and direction. And it's interesting, we were talking before this podcast about a relative paucity of scientists in leadership positions within the scientific funding enterprise. And I know you were on the NAILR committee that sort of looked at what should be done with scientific funding in Canada. And one of the recommendations was to have sort of some scientific planning in addition to public policy, because it is great to have translational products come out of research, but I think it can also be an overreach when we try to make products immediately out of science, because it doesn't always happen in a 3 or 5 year business cycle.
You don't want to be making your products out of today's science. You want to be making them out of tomorrow's science, because then you'll be competitive. And so from that perspective, you need a balance between the basic research that understands things at the cutting edge of the field and applied science, which makes it easy to then incorporate that in your products. And the people that are studying very basic things don't all end up as university professors continuing to do that and teaching people throughout their career. 75% of our graduates, we did a survey 10 years after we finished taking data on the Sudbury Neutrino Observatory project, 75% of them were in jobs that are completely different from academic professorial jobs. Everything from banks to government to medical research laboratories rather than physics laboratories, because they basically learned evidence-based decision-making, which is of value whether you're in a bank or whether you're doing basic science. And so they're also valuable in industry because your fondest desire as a company, if you're trying to decide what your next product should be, is to have somebody in your company who is capable of saying, you should pay attention to that discovery in Germany rather than the one in Japan, because it's more likely to be correct. And that's what we need at the cutting edge for our next product.
It's interesting. It's sort of like asking about the origin story, and it turns out it's not so much the where you came from, it's the people that you meet along the journey. And likewise, in the funding of science, you're not just funding something that eventually makes a electric car, you're funding the training of the people that actually will have the wisdom to not only make electric cars, but to decide how they should be best done, and many other secondary benefits that I think are hard for a government to quantify as they begin to do the difficult job of balancing where they spend their limited resources.
Absolutely right. And it's a mistake to think the Canadian industry is going to thrive if all they're doing is trying to use the information that already exists.
Yes.
Because things are expanding so quickly right now.
So we could go on and on, but we have one.
Yeah, I was going to actually ask the kind of, we've talked a lot about success and we talked about Nobel Prizes and the importance of this work, but just to change gear, we do actually always, we're very interested in finding out what bumps in the road that scientists have had. And I think it's good for our audience to know that it's not all plain sailing through science or anything else in life. So can you tell us about a bump in the road and how you managed it and how you interacted?
Well, certainly COVID was a major bump in the road for everybody's life. And at the time that COVID began in March of 2020, it happens that the director of a major project I'm involved in, and many of my colleagues here in Canada are involved in Italy, was in Milan and locked down because Milan was one of the early hotspots. Mm. And at that point, people in the ICU were destined to die, basically, if they couldn't get a ventilator to try to keep them alive. But ventilators were in very short supply. We were dealing with liquid argon, as I mentioned earlier, and his idea was maybe we can get the resources to convert our scientists to work on producing a new ventilator and perhaps developing something that's cheaper, fewer parts, and therefore dealing with a very limited supply chain during COVID. And so we managed to do that with a combination of people here in Canada. I was able to get strong support from the directors of major research laboratories here in Canada, Chalk River Nuclear Laboratories, Triumph Laboratory in Vancouver, SNOLAB, and scientists here at Queen's and a number of other universities. And so we had a product ready to be tested in about 4 months. And then it made me realize just how stringent the testing is in the medical field. Another 4 months of testing to deal with something that's going to take over breathing for someone, which was highly appropriate. But in 8 months, we had something that was ready to be manufactured, and we were able to provide thousands of them to the Canadian stockpile at about a quarter of the cost of typical ventilators on the market that are designed to do everything, not just a particular patient in a ICU who's suffering from COVID or another major respiratory disease. But ours was rather targeted. As I said, significantly less expensive and easier to produce. And all of the scientists felt they thought that what they did was very valuable because they were able to actually use their standard expertise to address the COVID problem that was overwhelming all of us.
I think it was through COVID. I think that we're very proud to have contributed to the literature with our own work on COVID. But I think it was a time for scientists to step up, and I think that your kind of your development of kind of a working ventilator within such a short time frame really underpins that interdisciplinary kind of nature of our fields that we discussed earlier about how, the science doesn't really have any demarcations. We help each other out to achieve common goals.
And we were very grateful to philanthropists actually who gave us money at the very early stages before we had a government contract to enable us to move forward. And there was a very strong response from such people here in Canada.
Well, thank you, Art, for being so generous with your time today. And we'd like to thank Dr. McDonald for taking us from the stars to the intensive care units and reminding me why I should have been a better physics student back in the day here at Queen's University, and also for sharing your thoughts about Canadian science funding, particularly for large projects. And before we let you out of here, though, and wrap up the podcast, we'd like the audience to get to know the person a little bit more behind all this research. So we're going to ask you some absolutely sort of salacious questions about winning the Nobel Prize, because we're geeking out on the science and we want some red carpet questions answered. So first, when and how did you first learn that you'd won the Nobel Prize?
Phone call at 5:15 in the morning, which my wife answered the phone and was about to say, "What do you mean? Call it." Anyway, I picked up the extension and I recognized the Swedish accents. I didn't by any means expect that. It was really about 14 years after our original discovery. And however, I was very happy to hear it and to accept the prize on behalf of the team that did the work. And great fun. Actually, the Whig Standard here in Kingston had a headline which was not "Local Man Wins Nobel Prize." It was "Not a Hoax."
High expectations indeed.
Yeah. Okay, so another burning question that I have for you is, what do they serve for dessert at the Nobel Prize dinner?
Oh, a beautiful combination of frozen delicacy, several of them of different compositions and colors, created in the form of a flower. Flowers everywhere. 1,500 people at the banquet.
Oh, wow.
Gold. I was going to say gold silverware, which was quite gold. Goldware and gold on the plates, and the prize winners are seated. I was seated between two princesses.
Oh, wow.
You are now too.
They're bad luck, but fascinating conversation. Very down to earth individuals.
So who accompanied you to this momentous banquet?
Well, normally you're allowed to bring 14 people, I think it is, and typically that's family members and other a few other people. But I learned from a colleague who had a large collaboration that there's another room where they have a few hundred seats, same silverware, same everything as in the main banquet, on a closed circuit TV coverage. And so I managed to finagle it up to 35 people, and therefore could take a lot of the very important colleagues and their spouses. That was very important too. That's what got us there, was the family effort. And we all stayed at the Grand Hotel and had almost the same experience. I mean, it's amazing. You walk out of a door to get into a limo, which they provide you to go everywhere, and there are actually paparazzi.
Wow!
For a few days, I actually had paparazzi there.
Wow!
You say, how did I ever get here?
So, what surprised you most about the whole process of being awarded, or the Nobel Prize, or the ceremony? What was the most surprising thing?
Well, the whole city of Stockholm is basically into this for a week, but what was really fun, along with everything else, was what's called the Student Nobel Nightcap. After the banquet, well, there's the presentations, and then the banquet, and then a ball another part of the main banquet location. And then starting at midnight, there's the thing the students run. All of the students are dressed the way the laureates are in tuxes and so on. Boy, I'd love to have the tux concession in Stockholm at that point. But, it was incredible. They had taken one of the buildings at the University of Stockholm and turned it into a landscape of the world. And then we were in tropical forests, and they had a lamb roasting on a spit outside. 3:00 in the morning, I was tasting a brand new Swedish-produced scotch with some good friends, listening to a fantastic jazz group. It was really...
It sounds like a very fun party, actually.
Wonderful.
It's not as stuffy as I think I'd imagined it. It sounds like a raucous affair if it's 3 a.m. and you're roasting a pig.
The students were very polite and decorous
of course.
In their approach to things. It wasn't getting wild at all, but it was good food and good company.
It's a nice celebration of decades of research.
So the last question that we have to ask you, and it's possibly the most important question, is if you were a cartoon character, which one would you be and why?
Oh, boy.
You knew you were coming on a heavy-hitting podcast.
Oh, this is
in fairness.
This is a very heavy-hitting podcast. Unfortunately, as I get older, I'm beginning to look more and more like Yogi Bear. And I try to keep my personality in that sort of a quiet, non-ebullient personality as well. So I'll take Yogi as a possibility.
Fantastic. Well, I would actually posit here that maybe you're smarter than the average bear.
That's right. Says Boo Boo.
Dr. McDonald, thank you on behalf of Dr. Archer and myself for taking time to talk to our audience today about your thoughts on Canadian science and your very groundbreaking and important discoveries. I'd like to thank our listeners also for taking the time to get to know Dr. McDonald with us, and we really hope that you enjoyed the show. If you enjoyed this episode in particular, or you'd like to know more about the research at Queen's University, or to share this podcast, you can search for Time to Talk Science and Medicine wherever you normally look for podcasts. Thank you very much.